Yep, we are rolling. Cool. So what were we discussing? We were discussing the syntax and semantics of propositional logic last time, right? So last time well, we finished the syntax of propositional logic, and then we got into like how to build truth tables and stuff like that. So all of that is sort of part of the semantics of prop logic. So semantics, like roughly, it just means that um, it's basically like having sort of a vocabulary um, that helps us sort of understand how each of the like the operators and all of the stuff operates. Like, so I'll just add a border here. Ayo, why did this? For some reason it just whatever. Okay. Okay. So even though I'm mentioning syntax like below, all of this stuff is part of syntax. Um, so syntax. Oh, sorry, not syntax. Semantics. We are doing semantics. Semantics of obviously prop logic. Um, yeah. So we already sort of like know what like a compound proposition or like a complex proposition is. Like, so an atomic proposition is just like P, right? But like a compound proposition will be like some P and like some kind of um, like there are like more than one propositions in a compound proposition. So something like P implies Q or P or Q. All of these are like compound or complex propositions. So we know that there are like certain operators, and we have already discussed the operators. But to sort of summarize that and to put things a bit more um, in a concise manner, right? What we'll do is we'll construct a table. Okay. Logical operators. And what we'll do, let me actually just move this a little bit inside so that I can use this. So we have logical operators, that's the first column, and then we have the truth conditions. So we'll just construct this table, and that will sort of summarize the semantics. Because when we are constructing this table, we are sort of defining what each of the operations mean. So obviously the first one is like the negation, right? So and here the truth. So I'll just sort of like define the truth condition. So a truth condition is basically an answer to the question when is one sec. When is it true? Okay. So it's just like this question is answered by the truth condition. So when I ask you what is the truth condition for some proposition, or sorry, for some operator, uh, the answer will be when it is true, right? So for example, not p is true when p is false. One second. P is false. Why is my computer acting up? Okay. Yeah. So this is the truth condition. So the truth condition for not p is false. Okay. And then we can go on to like each of the other propositions. Sorry, the operators. So you can tell me what is the truth condition for p and q.
So when P and Q are both true for the conjunction.
Yeah. So when you're writing out the truth conditions, you will write them like very like in a more like elaborate manner. Like so you will write p is true and q is true. Okay. So all of this stuff is based on the the truth table of each of these operators. Um, so what about p or q? An inclusive disjunction.
So P is true or Q is true, and then or both of them are, well, yeah, I guess you can just write P is true or Q is true. Yeah.
Yeah. Okay. So the next one is p x or q.
So here we have a disjunction. So it's uh so so it's very similar to the one above,
Yeah.
and in this one, so can you say like one out of P and Q is true?
Yeah. So I'll just put these quote marks to denote that it's the same. Okay. And then uh this is true obviously, and uh, you could say that like at most or exactly one of them is true. So or you could just write p is true or q is true and p and q is false. So and p and q is false. Okay. So this is this is true or this is true, but both of
Yeah.
them is not true.
Mm-hmm.
Yeah. So that will be like the truth condition. Um, what about this one?
So it's true as long as, so the one exception where it's not true is when the antecedent is true and Q is false.
Yes.
So you can just say when like P is true. So when P is, so yeah, if P is true and Q is false, then that's gonna be false. So
Yeah, but
I'm
we
not
are
sure
looking
if
for the
you
truth
want
condition.
the opposite of that.
Yeah.
But yeah, I'm not sure how you could put that in words, but so
Okay, so um, what you can say is that P is false or Q is true. So I'll show you the quick proof over here, but then I'm just doing this in passing because we will get back to this later. Um, so this is what we want to prove, right? Not P or Q, right?
hmm
So the only um, the only place where this is false, right? The only place where not P implies Q is false is when
so when the antecedent is false and the
no,
oh when not, so when the antecedent is true
yes,
and Q is false.
yeah. So not P implies Q is true when P is true and not Q is false. So what I will do is like we do in math, we multiply something by 2 on both sides of the equation, right? So
Yeah.
I'll just negate both of the sides. So on this side we will get not, so not P implies Q, and that is like equivalent to not P and not Q. Okay. And this, so this gets double negations are neutralized, so we are left with P implies Q. uh, oh sorry, and then you're left with this, right?
hmm
And
And then you just
here,
multiply it out.
sorry,
You just multiply it out.
yeah, exactly. So how we do in math, we'll just multiply this by each of the elements. uh, so you will get, so this is actually called De Morgan's law. So you get not P, and this will be Q, and this and will convert to a disjunction, and this is what we called De Morgan's law, right? We will cover De Morgan's when we are doing rules of replacement, so you don't need to remember this right now because we will eventually get to it. But yeah, basically this is how we can sort of prove that this is equivalent to this. The obvious other way is to just draw a truth table for P implies Q. We know what that is. That will be true, false, true, true, and then you just negate it. So when you negate it, you'll get false, true, false, false. And when you do the not P, so not P or Q, right? So you draw the truth table for that, you'll basically have the same thing. You'll have the
Just
same thing as P and this one.
so
Uh,
they're just at the end.
yeah, this one. You'll have this.
Okay.
So that's another way, like you can prove it by multiple in multiple ways. uh, but yeah, so this is like a short proof, but I like you can completely like just not write it, but just remember that that's how we get the truth condition for this. We get the truth condition for the implication by doing all of that, and the truth condition is antecedent is false, consequent is true, or consequent is true.
Okay. And the one above for the
Yeah, this one.
there a proof we can do there?
We can do that, sure, but I mean, so one second, let me just. Right, so this is like you can just do this by just looking at like what the operator just means, right? Like that's why we are defining these like truth conditions. um so that, like it's just what this operator means. P is true or Q is true, and this is true. So for example, uh, if you draw the truth table for this, you will get uh, false, true, true, false, right? And you can see that when at least one is true, it is true, but when this is when this both of them, when P and Q is true, this is false, so it's not P and Q. So you can sort of get a proof like that, but yeah, we will do proofs later on. But like because like this is a bit more unintuitive, that's why I went for the proof here. um Anyway, like the this is this kind of stuff will be like an exercise later on. Okay, so the next one is P double implies Q. What would be the truth condition for this? Hello, hello, can you hear me?
Yeah.
Yeah.
Can you hear me?
Yeah, I can hear you now, but like you
Yeah.
were, I couldn't hear you for like the last 10 seconds.
Okay. Yeah, maybe my mic was on mute. I don't know.
Okay.
But so when they both have the same truth value, so when P and so when P is true and Q is true, or P is false and Q is false, would it be like that? When they
Uh,
both have the same, can you hear me?
yeah, yeah, I can hear you.
Yeah. When they both have the same truth value.
Yeah. Yeah. So you can, so how would you write the truth condition for this?
All right, as P is true
Okay.
and Q is true, or
Okay. Or what you can do is you can specify two different truth conditions. So this is truth condition one, and then this is truth condition two. Okay. Or
P is false and Q
mhm.
is false.
Okay. Yeah. Yeah. So that's just like sort of like a brief overview of the each of the truth values and all of that. Um, we have already talked about um getting like the we have like using uh, like each of the truth tables. We have already done compound propositions and their truth tables and all of that, right?
Yeah.
Yeah. Okay.
Uh, but we've done it, yeah, and like we've done different examples.
Okay. Hmm. Yeah. 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 Okay. So I guess that's yeah. I think that should be enough for like the um for like just the semantics. But yeah, like you can add that over here, like both have. Hey, what the hell? Okay, have the same value. Yeah, that should be good enough for like semantics. Okay. Um. Yeah. So I guess we can move ahead to something more interesting. And so we have already done two tables. We've already done like compound complex propositions or atomic propositions. We've sort of like formalized how we can draw like a truth table and all of that. Have we covered tautologies and contradictions?
We briefly covered them, yeah. So we briefly like we drew out an example of a tautology, and we said that all rows of a truth table are true,
Yeah.
and then a contradiction is a proposition where all the rows of the truth table are false.
Yeah.
And so that's what we've done with
So
tautologies.
and what so we have like two extremes, right? One where everything is true and one where everything is false. What if you have like a mixture? What would that be called? Did we discuss that?
Nope, we didn't.
Okay, so those will be called contingencies.
All right. Yeah, we haven't covered that for sure.
Yeah,
I
okay.
don't think.
You can add that. So we have tautologies, we have contradictions, and then we have contingencies. So contingency is at least one row of the truth table will be true and at least one will be false.
Okay.
Yeah. So it has to have like a mixture of both true and false truth values in the rows, and that's when it will be like a contingency.
Yeah, makes sense.
Yeah. So okay, so that is out of the way. Contingencies are done. Um, okay. Did we talk about whether like when two particular statements are consistent? What that means?
Doesn't ring a bell to me.
Okay. So let me just write that here anyway. Okay. So first is contingency. Um,
The contingency, at least one row is true and at least one is false, right?
yes. A contingency. At least. Oh, what the hell? At least one row is T and at least one is F. Okay. So that is one concept. Of course, tautology. So I think yeah, this is all part of like the vocabulary, right? So this is all part of semantics. Um, Tautology is all rows two true. Contradiction um, all rows false, and then okay, consistency. So consistency, like you would say a proposition is consistent if at if it's not a contradiction, basically.
Yeah, I'm following.
Okay. So yeah, like that's also like sort of how we generally, like in daily usage, we use consistent. Like, consistent just means that there is no contradiction. Um, yeah. So two statements, two props are consistent uh, when their truth table is not all false. Okay. So all it needs for a proposition to be consistent, or for two propositions to be consistent with each other, is that there is at least one t in that entire thing. So the entire thing could be false, but even if one row is true, it is consistent.
So you mean the compound proposition formed by two atomic propositions, right?
Yeah.
So yeah, it's like the compound proposition formed by two single atomic proposition is consistent when their truth table is not all false.
Yeah.
Okay.
Yeah. And there are some general forms. Okay. The general form of a tautology is P or um, not P. That is a general form. So any tautology. Now this P can be replaced with. Oh, I'll just use like metalinguistic variables, so that it represents any well formed formula. Uh, yeah, tautology is alpha or not alpha. Uh, Contingency could be like alpha or beta, or any other. Basically, it could, like, contingency can be anything. It doesn't have to be like a disjunction. It could also be a conjunction. Um, Etc. A contradiction is alpha and not alpha. So P and not P, Q and not Q, S and not S. Those are all contradictions. But P and not Q is not a contradiction. P or not S is not a contradiction. It's a contingency. And consistency, like, there's no general form because it's not a, like, it's not a kind of, like, it's not a proposition. It's a property of propositions. Um, like, two propositions are said to be consistent when their truth table is not all false. So that we have done. Yeah, I think that should be good enough. Um, yeah. So we'll just move to the next part, which is more fun. Um, I'll just draw a line here. Okay, and now we can talk about properties of arguments. Yeah, talking about the properties of argument. So we've already discussed what an argument is. We have made like certain definitions, and we have made some revisions to those definitions, and we have arrived at like newer definitions. So our latest understanding was um, a set of well-formed formulas such that at least one well-formed formula is a premise and at least one well-formed formula is a conclusion. That's what an argument is. That's what we have defined so far. And then what we'll do is we have defined an argument, but we haven't given like a description of an argument. So that's what we're going to give. We're going to describe arguments by sort of delineating their properties. So an argument can have certain properties. One is validity. Why did I write in all caps? I'll just write validity. Okay, the first one is validity. The second one is soundness. Okay. Yeah. So there could be other, there could be other properties, but right now let's focus on validity and soundness. So let's just define validity. Okay. And more specifically, this is called deductive validity. One second. So this is deductive validity and this is soundness. So I'll just write D, okay, D validity. D validity. So like we can sort of understand that an argument is like deductively valid if what it means is that the conclusion of the argument follows from the premises, right? And so, but that's like a bit of like a vague understanding of validity. So something more clear is what we can do is we can sort of default to the usage of truth tables to define what validity is. Like we can say, oh yeah, like this is like there are certain inferences where the conclusion follows from the premises, and some conclusions where the conclusion does not follow from the premises. So we'll just use like a truth table to define what validity is. And for that, what I'll do is I'll draw the truth table for an argument. Okay. Let's write the argument out. So the argument is P1, P implies Q. Now this could be anything, doesn't matter. P2 is P, and conclusion is therefore Q. Okay, this is the argument. Now what we do is we draw the truth table. So how many variables there are there?
2.
So that's P and that's Q. Okay, so we write true, true, false. I hope you remember the formula to write the truth values. uh, so we have this, and we have another one for P implies Q, so that will be true, false, true, true. So this is where our premises start. Okay, so this is where it starts. I'll just make this a thicker line to denote it. The second premise will be just P. I know, like, it's a bit redundant, but I'm just copying that over here. Because like P is in the argument, so I'll just rewrite it for the sake of clarity. So that's just T, T, F, F. Okay, and then you have the conclusion, which is Q. Okay, and the conclusion just is the same. Okay, so that's T, F, T, F. Now I want you to observe all the places in the argument where both the premises are true. How many places are there?
So when you say both, you mean all of the premises?
Yeah, this one and this one. So there are two premises, right?
Yeah, and
Yeah.
yeah, the conclusion's also a proposition, but not a premise.
Yeah, it's not a it's a proposition, but it's not a premise.
So in how many places? I can just see the first row.
Right.
So one place.
So this place, you can see that if both of them are true, this is true. But now let me give you an example of a different argument, just like the exact same argument with a slight twist. So I'll just copy paste this over here. And now what I'll do is I'll modify premise 2 and the conclusion. Okay, I'm adding a negation to both of them. Now let's redraw the truth table. So we have P, we have Q, we have P implies Q, we have not P, and we have not Q. So this is true, true, false, false, true, false, true, false, true, false, true, true, false, false, true, true, false, true, false, true. Okay. Now I want you
Yep.
to point out all the cases where both of the premises are true.
So it's at the bottom now. So not P and not Q. They're true at row number 4 on the bottom.
Okay. Any other?
I cannot see. I'm just looking at the two last columns where they're both true.
No. So this is the premise, right? This is P1.
Yeah.
This is P2.
Okay, I got confused with the I
Yeah.
was thinking of the
This is the
conclusion.
conclusion. Yeah, don't look at the
Yeah.
conclusion.
Yes. So then two places then. Yeah, the
Yeah.
third row as well.
Yeah. But if you notice here, the premises are true. Both the premises are true, but the conclusion is false. And this is like an important distinction between this argument and the previous argument. In the previous argument, wherever you observed the premises being true, the conclusion was always true. Now this was a relatively small argument, but if you try like a larger argument with more connectors and more operators and all of that, you will see this happen uh, more clearly. Um, but even in this case, just like with a couple of modifications, you've produced this. The premises are true, but the conclusion is false. And this is what we call an invalid argument.
Yeah, I was looking at the argument and it wasn't in the form we gave for an argument.
Right. So this is invalid. So now we have a concept of what invalid means, right? The concept is when even one, like if there is a single case where the premises are true and the conclusion is false, then the argument is invalid. So we can just flip that upside down to get the definition of validity. So let's just go and write here. So an argument is deductively valid if and only if an argument is valid if and only if the premises are true, then the conclusion is or must be true. Okay, so whenever if an argument is valid, that means that if the premises are true, then the conclusion must be true.
Yeah.
And in so we can just flip this to get invalidity. Invalidity is when an argument is invalid if and only if when the premise if and only if uh, when the premises are true, uh, there is at least one case where the conclusion is false. So
Yeah.
these are all like like each of them is like a counterfactual world, right? Like a counterfactual world. So one world where both of the premises are true. The second world is when the first one is true and the other one is false. So these are all different possible worlds. Um, and basically the idea is that there is no world. An argument is valid when there is no world such that if the premises are true, then the conclusion is false. And an argument is deductively invalid if there is if there exists even one single word where the if the premises are true, then the conclusion is there is one case where the conclusion is false. Okay, you following that much?
I think so, yeah.
Okay, can you
You could just go up a tiny bit.
yeah,
Like when you were keep on going up
okay.
where you wrote. So what does it mean where you wrote the I with double F?
Oh, if and only if.
Okay. So an argument is valid if and only if uh if the premises are true, then the conclusion must be true.
Yeah.
So it's basically, so if I understand correctly, it's that all the premises are true, including the conclusion, which is also true.
No. So the idea is wherever all the premises are true, the corresponding column for the conclusion must be true.
Okay.
If it is false, if there is even a single case where it is false, then the argument is deductively invalid.
All right.
Yeah. Okay. So yeah.
So
Like
then
yeah.
this, yeah. So then this one is deductively invalid because there's one case.
Exactly. So even though you have this case, right? You have this case where both of the premises are true and the conclusion is true. But you also have this case where both of the premises are true and the conclusion is false. So that's why this is an invalid argument.
Yeah, I think I'm tracking. Yeah.
Yeah.
So yeah, that's the validity of the argument.
Yeah.
So
You
you
can
draw it
also put
out.
it in different ways. So, for example, an argument is valid. So, if an argument is valid, then it is impossible for the premises to be true and the conclusion to be false. That's another way to put it.
In the truth table
Yeah.
for all the rows. Yeah.
Yeah.
But like you don't want at least one instance of it.
Yeah.
Yeah, I think I'm okay.
Yeah. So there are a bunch of valid forms of forms of argument forms which are considered valid in propositional logic, and those will be what we call the rules of inference. So each rule of inference is an example of a valid argument, and that's what we will cover eventually in the next session. But for now, yeah, in this case, what you have generated in this invalid argument, right? Oh yeah. Sorry, yeah, I missed one thing. So yeah, in the next one we will cover each of the valid forms in propositional logic. And we will also cover the invalid forms just for practice, because there are only a couple of invalid forms which you can easily understand. Okay, so in this case, when you are showing that an argument is invalid, you are generating this case, okay, this case such that the premises are true and the conclusion is false, and this is what we call counter example generation. So you have generated a counter example. Okay, so this is called a so in any truth table, right, of an argument, if you see this, if you see premises being true and the conclusion being false, that is a counter example. So a counter example like is just that a case, it's just a case where the configuration of the premises is true and the conclusion is false, and you can basically make a counter model out of it. The counter model will be this. So this will be the counter model. We will discuss this later. Let's not get too technical right now. When we draw truth trees and all of that stuff, it will become even more clear. Okay. So you follow what a counterexample is? Can you just relay it back to me?
So you're effectively drawing a truth table for the argument,
Yeah.
and then once you identify a case where the premises are true and the conclusion is false, it means that the overall the argument is invalid, and the specific case is which invalidates the argument is known as the counterexample.
Yeah. Oh wait. What's the counterexample?
So the specific so the case where you have two premises which are or just the premises in the argument which are all true,
Mm-hmm.
and the conclusion is false.
Yeah.
That's the an example which like invalidates the
Exactly.
argument, and it's known as a counter example.
Exactly. Yeah, that's the counter example, and the counter model basically is what are the respective truth values of the of the premises. Sorry,
Which
not the
leads to that.
premises. Each of the
Yeah.
propositions.
Yeah, so the two propositions which lead to the counter example in the same row. Yeah.
Yeah. So these yeah p. So what's the truth value of each of the propositions? So p will be false and q will be true. So that is the counter model. Okay. So there are a bunch of ways to evaluate validity. Okay.
And that was one we did, right?
Yep. Okay. So one is what we did. One is a truth table. The other is a truth tree. And then you have natural deduction. Wait. Yeah, natural deduction. Uh, yeah, those are like the methods of basically determining uh, whether an argument is valid, and these are all like more or less sort of like rigorous and mathematical ways to prove it. So for example, I can show you the example of like a truth tree just to get you excited, but we will explore truth trees later. um, um, yeah. So what I've done is here I've negated the conclusion, and then I'll move one premise by one premise. So this there will be a split, uh, and then you will be like P, and then you will be like P. Sorry, you won't do that. So there is P. So this branch is closed, this branch is closed because there's a contradiction here. So this branch is closed, there's a contradiction here, so this branch is closed, and when all the branches are closed, this argument is valid. But on the other hand, if you do something like, if the conclusion is this, if the conclusion is, if the argument is this, not P, therefore not Q, and here I've negated the conclusion, you will get not P or Q.
So
Here,
I'm not really tracking what you're doing
yeah, I'm
exactly.
just showing. I'm just showing you the like how a truth tree looks basically. We will discuss how to draw truth trees in detail later.
Okay.
I'm just
Because at the
like
moment, yeah, at the moment I'm not really tracking like what's the premise, what's the conclusion,
yeah,
what you're doing.
yeah,
But
yeah,
I guess as long as we see it later.
yeah. We'll see. So, but yeah, this is how like a truth tree looks like. And here both of the like both of the branches are open. We will discuss what open means and all of that. So this argument is invalid. So that's how like a truth tree looks like. So I'm just like showing you just like an illustration of what a truth tree is. Um, okay. So yeah, so this is validity, and soundness is a very simple concept. And that's so we'll just finish soundness and then we can call it a day for now. But soundness, so soundness is basically validity plus true premises. Okay, and this is where most of the debating happens. So most of the debating happens with respect to determining the soundness of an argument. Like somebody could deliver an argument that is valid, right? But the question is, are the premises actually true? So, for example, um, if Patrick is a cat, okay, if Patrick is a cat, I'll just not, I'll just write this, okay. If Patrick is a cat, then, um wait one sec. If so, P is Patrick is a cat, okay. Or I can say C. Let's just call it C. Um, so C implies T. If Patrick is a cat, then Patrick has a tail. Patrick is a cat, therefore Patrick has a tail. So this is a valid argument. It's similar to the form that we used before. This is a valid argument, but there is one premise, namely this one, which is false. Patrick is not a cat. So even though this is a valid argument, it's not a sound argument, because soundness of an argument means that the argument is both valid and all of the premises are true. Okay?
Yeah.
So you can also get like a relation from that. So the relation will be like all sound arguments are valid, but not all valid arguments are sound.
Yeah, I'm tracking.
Yeah, so I'll just write that as well. All sound arguments are valid. Not all valid arguments
Sound.
are sound. So yeah, So that's just what validity and soundness is, and this is like going to be a very crucial distinction, like when we go forward for like debating or whatever, because you can have um like if somebody just presents to you an invalid argument, there's just no need to like analyze each of the premises and check what the truth value of each of the premise is, because if the argument is not valid, then it's definitely by definition not sound. So whenever somebody presents an argument, the first thing that we would check is whether the argument is valid. And once you have confirmed that the argument is valid, then we proceed to checking the premises. Because otherwise, if who cares if the premises are true if the argument itself is invalid? Like, even if you have true premises, it's not going to entail the conclusion. Um,
So the second sentence, not all valid arguments are sound. It makes I see what you're saying. Yeah, so basically any invalid argument is not sound.
Yeah, any invalid
Yeah.
argument or any valid argument with a false premise
Yeah.
is not sound. So you can have a set of valid arguments, but those arguments have false premises, and because of that they are false. Because of that they are not sound.
But can an invalid argument be sound?
What do you think?
Well, so if all the premises are true, then I would if based on the definition of soundness that all the premises are true, if an invalid argument, I would my gut feeling is based on what you said, no, but my gut feeling is yes.
Yeah, it can't be sound. So think of this as a conjunction, okay? Soundness is a conjunction of validity and true premises. So the
Oh,
argument has to be valid.
okay, so it's both got in them. Okay,
Yeah.
okay, so it's dependent on both validity and true premises, the soundness.
Yeah.
Okay,
Can a
yeah.
sound argument be valid?
So yeah, so a sound argument is valid if the premises are all true.
Yeah. Can an invalid argument be sound?
No,
Why?
because soundness depends on validity.
Yes. Validity is a necessary feature of soundness. Like by definition, it has to be valid.
Yeah. Earlier on, I was thinking them as two separate things, but yeah, I see now with your definition that it depends on both.
Yeah. It is a
Yeah,
conjunction
validity.
of the validity and true premises, not a disjunction.
Cool.
Yeah. So yeah. So valid argument. We can just like do a recap. Valid argument is an argument is valid if the premises are true, then the conclusion must be true. An invalid argument is where it is possible for like the premises to be true, but the conclusion to be false. Um, yeah. So that's like the distinction of yeah, we talked about the distinction of valid and invalid. Sorry, the sound and unsound. Sound is when an argument is both valid and all the premises are true. So I'll just add that as well. Um, it has to be all the premises have to be true. Like even if a single premise is false, it'll be unsound. All true premises. Um, so yeah, I guess that should be enough for today. And in the next session, what we'll do is um, we'll proceed to rules of inference.
Great. Yeah, that's what I had on the schedule.
Yeah.
All right. Cool. Yeah. See you next time then.
Yeah. See you next time. I'll just end the recording.